This is part one of the series Integration. In this series, we're going to investigate the second major branch of calculus, which is known as integral calculus. And the fundamental problem in integral calculus is known as the area problem. We're going to start out this discussion by talking about a topic known as anti-differentiation. Now, it's going to seem at first as though anti-differentiation is very unrelated to the area problem, but you're going to see in a very short period that it's intimately related to what we're going to be working with when we deal with integral calculus and the area problem. So to begin with, let's say that we wanted to find some function capital F that has the function f of x equals 3x squared as its derivative. Given what you now know about differentiation, you would probably say that that function is x to the third. And that's because the derivative of x to the third is 3x squared. But then again, you also know that the derivative of x to the third plus 4 is 3x squared. And in fact, any function of the form x to the third plus some constant c is going to have 3x squared as its derivative. And so you can see here that all of these functions, the x to the third plus c, they are a family of functions that are simply vertically shifted from each other. So whether it's x to the third plus 4 or x to the third minus 4, they all have 3x squared as their derivative. And as such, those functions are all called antiderivatives. So as a quick recap, all the functions of the form x to the third plus c are antiderivatives of the function 3x squared. And they are called a family of functions. Notice that we have here an antiderivative. All these functions are an antiderivative because there's not just one. It's a family of functions. Very important point that antiderivatives are families of functions. And we're going to use that as we move forward through our discussion. So let's look at antiderivatives a little bit more formally. A function f is an antiderivative of f on an interval I if f prime of x equals f of x. That is, if the derivative of the antiderivative is the original function f for all x in I. Now, the way we represent antiderivatives, if big F is an antiderivative of little f on an interval I, then big G is an antiderivative of f on the interval I if and only if G is of the form g of x equals f of x plus c. This is simply saying that if f is an antiderivative, G is an antiderivative if it's a vertical shift of that first antiderivative. And that's related to the concept that we were just talking about in the previous set. Now, this type of equation may look a little different because we're using capital letters instead of lowercase letters, but we should be relatively familiar with this from our discussions of differential calculus. The symbolism is a little bit different, but the concept is the same. And what we're dealing with here is a derivative on the left and a function on the right. Now, you should be familiar with that in something like this, where we had y equals 3x to the third plus 2x, and then we took the derivative, so we said y prime equals 9x squared plus 2. This is a similar form to this. We have a derivative on the left and some function on the right. And this particular form is known as a differential equation. And a differential equation in x and y is an equation that involves x, y, and derivatives of y. So again, for example, y prime equals 3x squared plus 2 is a differential equation. And this differential equation is the derivative of this function. This function is called the general solution to the differential equation. So we're working backward in this case. Ordinarily, we would start out with y equals x to the third plus 2x plus c and say, what is the derivative of this? This differential equation is the derivative of this function. Therefore, this is the general solution to this differential equation. So we're finding out the antiderivative of this is the general solution to this differential equation. It's a little bit twisted, but I think you'll get used to it after a couple of tries. Now let's take a look at this a little bit more symbolically. When we're solving differential equations, we will have often this form that we're dealing with. If we started out with something like this, y equals 2x to the third plus 3x plus 3, let's say, and we wanted to take the derivative of this with respect to x, ordinarily we would say this. Derivative of y with respect to x is 6x squared plus 3. And we're going to rewrite this in its differential form. So dy equals 6x squared plus 3 dx. This would be the differential form of this differential equation. And when we're solving for differential equations, it's often more convenient to work with it in terms of its differential form rather than in its Leibniz form. Now, the operation of finding all the solutions of a differential equation is called antidifferentiation or indefinite integration. And we denote this by this strange-looking S-type shape. This is called the integral sign. And the part immediately to the right of the integral sign is called the integrand. This dx in the differential form denotes the variable of integration. What are we integrating across? The big F is the antiderivative of f, and c is the constant of integration. Now, before we can put any of this into practice, we're going to need to get a handle on the basic rules of integration. So let's take a look at those. To start out, we have a restatement of the definition of antiderivative, that the derivative of the antiderivative is the original function. So this big F is the antiderivative, and that prime denotes the derivative of the antiderivative is the original function. Another way to say that is the indefinite integral of the derivative of the function is the original function plus some constant of integration. So the antiderivative and indefinite integral are synonyms, and the antiderivative of the derivative is the original function. In a very crude way, this is similar to saying the square root of something squared is that thing. This square root is undoing the square. And so you have here an antiderivative is undoing the derivative of the function. So these, again, in a very crude fashion, these are analogies of each other. So we have integration is the inverse of differentiation. And if we look at it from the opposite perspective, if the antiderivative or indefinite integral of some function f with respect to x is this big F, then the derivative of the antiderivative is the original function, which of course means that differentiation is the inverse of integration. All that to say that antidifferentiation and differentiation are inverse operations of each other. That's a fundamental concept that we need to get a handle on before we can really start to grasp any of the deeper implications of integral calculus. Now let's take a look at some of the basic mechanical rules of integration. Now, I know that this may seem a little overwhelming at first, but try not to panic. It's not as bad as it may first appear. Let's take a look at the very first relation. Here we have the derivative of a constant. We know that the derivative of a constant is 0. If we take a look over here, the integral of a constant, or the integral of 0, is a constant. So there is this inverse relationship here, that the derivative of a constant is 0, so the integral of the 0 is a constant. Let's take a look at the second one, and maybe the pattern will start to become clearer. The derivative of a constant times some variable of differentiation is equal to just the constant. Therefore, the integral of the constant is the constant times the variable of integration. So you should be able to see a pattern forming here, that we're moving from derivative of a constant is 0, therefore the integral of the 0 is the constant. So there's this back and forth relationship here. Same thing here. The derivative of a constant times the variable is the constant, so the integral of the constant times the variable of integration is the constant times the variable. So there's this back and forth inverse relationship working between differentiation and anti-differentiation, which is also known as definite integration. So let's take a look at the next one. We have a constant times a function of a variable of differentiation equals the constant times the derivative of the function. This is the constant multiple rule. Over here, we have a constant times a function, and we take the antiderivative, and we have a synonym, or an analogy actually, to the constant multiple rule for integration. So you just pull out the constant and take the antiderivative of the function without the constant involved. So these two are very closely related as well. The next one, we have the derivative of the sum and difference of multiple functions is the derivative of the individual sums or differences. Here, the integral of the sum or difference of functions is the sum or difference of the antiderivatives of those individual functions. So again, very close relationship here in this inverse relationship. Here's the power rule of differentiation. The derivative of x to the n is n times x to the n minus 1. You pull the n out front, subtract 1 from the exponent. There's another inverse relationship working here. If we have the integral of x to the n, instead of subtracting 1, we're adding 1 to the exponent, and we're dividing instead of multiplying, all inverse operations here, and we're dividing by this n plus 1. So everything is working in an inverse relationship. Now there's a caveat here that n cannot be equal to negative 1. Obviously, if n were negative 1, this would be undefined because negative 1 plus 1 is 0. Now this same inverse relationship is present in our trig functions. The derivative of sine is cosine, so the integral of cosine is sine. So they work back and forth. The derivative of cosine is negative sine, so the integral of sine is negative cosine. Notice they're opposites of each other. Since the derivative of cosine is a negative sine, the derivative of sine is a negative cosine. This is kind of a confusing one until you get used to it, but if you think about it, it makes some sense. Derivative of tangent is secant squared, so the integral of secant squared is tangent. Derivative of secant is secant tangent. Derivative of secant tangent is secant. Derivative of cosecant is negative cosecant cotangent, so the integral of cosecant cotangent is negative cosecant. And finally, the derivative of cotangent is negative cosecant squared, so the integral of cosecant squared is negative cotangent. Now you'll notice that we don't have all the integrals of these derivative functions. We don't have the integral of tangent. We don't have the integral of cotangent. We don't have the integral of secant and cosecant. Those will come in future installations. So you may want to spend some time to absorb these rules, and then let's go ahead and try to solve a basic differential equation.